Once again, welcome to another edition of Subject Marks. Don't forget to subscribe to this channel. Today we will be treating past questions on energy quantization. Okay, so the first question we have here says an atom radiates 1.5 times 10 to the power minus 19 joules when an electron jumps from one level to another. What is the wavelength? So we are asked to find the wavelength. We are given the Planck's constant and then the speed of light. Okay, so we are asked to find the wavelength, which is lambda. We are given the E, which is 1.5 times 10 raised to the power minus 19 joules. Okay, we have our Planck's constant and then we have the speed of light. So we'll go ahead and slot in this formula, which says E. You recall that E is equals to hc over lambda. So if you make lambda the subject of the formula, that will give us lambda is equals to hc over E. So I'll go ahead and put this in our formula. Our H is the Planck's constant, which is 6 times 6 times 10 raised to the power minus 24. Then the C is the speed of light. That's 3 times 10 raised to the power 8. All over the E, the energy, that's 1.5 times 10 raised to the power minus 19 joules. Okay, so by the time we've multiplied this, we have 1.32 times 10 raised to the power minus 6 meters as our wavelength. So wavelength is equals to, I'm just going to write it up here so that we can see our answer is equals to 1.32 times 10 raised to the power minus 6 meters, which is the required wavelength. Okay, so the second question here says that an electron makes a transition from minus 1.60 electron volts to minus 10.4 electron volts. Calculate the energy loss due to this transition. That is the difference in energy. This one is a very, very straightforward question. So we go ahead, write out our parameters. Our E1 from here is equals to minus 1.60 electron volts. Our E2 is minus 10.4 electron volts. So the energy loss or the change in energy, you recall from our formula, is equals to E1 minus E2. And that will give us minus 1.60 EV minus 10.4 EV. So this is 1.60 EV plus 10.4 electron volts. And this will be equal to 8.8 electron volts. So the energy loss is equal to 8.8 electron volts. The third question here says energy associated with the photon of a radio transmission has. So we are given the frequency and we are asked to find the energy associated with the photon. So we are actually asked to find E. This is frequency in Hertz. We are given the frequency in Hertz. And then we are also given the Planck's constant. So you recall the formula E is equals to HF. So we go ahead. Our H is the Planck's constant. F is the frequency. And that will give us 1.989 times 10 raised to the power minus 28 joules. Approximately, this is 2 times 10 raised to the power minus 28 joules. So the energy associated is equal to this. I believe that is explanatory. Now, the next question says, if the frequency of an emitted X-ray is this, also we are given the frequency from this question. We are given the charge and then we are given the Planck constant. So we are asked to find the accelerating potential V. We are asked to find V. So you recall that EV is equal to HF. So we are asked to find V. So we make V the subject of the formula from here. So V is equal to HF over E. Our H is 6.63 times 10 raised to the power minus 34. F is 1.6 times 10 raised to the power 16. And our E, which is the charge, is 10 raised to the power minus 19. Altogether, this times this divided by this will give me 66.3 volts. So the accelerating potential is equal to 66.3 volts. Question 5 says a 500 kilovolts is applied across an X-ray tube. Calculate the maximum velocity, Vmax. Okay, so from here we have 500 kilovolts. So if you change this, kilo is 10 raised to power 3. So we have 500,000 volts. So you recall from this formula that EV, electron volt, is equal to half mv squared. This is for the kinetic energy. The maximum velocity, this velocity, is what we are asked to look for. So if you make it subject of the formula, we have V is equal to, if you make this particular V the subject of the formula, we have V is equal to 2eV over n. Okay, so this is the formula we're working with. Therefore, V is equal to 2 times our E. Our E is equal to 1.6 times 10 raised to the power minus 19. We know that already. That's the charge. 1.6 times 10 raised to the power minus 19. Then our V, which is 500,000 over M. And already we know that our M is 9.1 times 10 raised to the power minus 31. You asked me that, how did I get that? That's the mass of an electron. It's 9.1. That's the standard mass. Okay, so if you multiply this and find the square root, we have 4.2 times 10 raised to the power 8 meter per second, which is equal to the maximum velocity. So take note, the standard value of n, mass of electron, is 9.1 times this, and the charge on an electron also is 1.6 times 10 raised to the power minus 19. Okay, so the question 6 says, what is the uncertainty in the measurement of time? What is the uncertainty in the measurement of time? If the uncertainty in measuring energy, this is that of energy, and this is the mass. Okay, so from this question now, uncertainty in the energy is 2.45 times 10 raised to the power minus 19 joules. We have the mass and we have the Planck's constant. So you recall, we are asked to find delta T, which is uncertainty in measurement of time. So you recall that delta T, delta E is equal to H according to the uncertainty principle. So if we make T the subject of the formula, we have H over delta E. Our H is the Planck's constant, which is 6 times 6 times 10 raised to the power minus 24 over change in E. That is 2.45 times 10 raised to the power minus 19. And if you divide this by this, we have 2.69 times 10 raised to the power minus 56. seconds. So the uncertainty in the measurement of time is that 2.69 times 10 raised to the power minus 15 seconds. Question 7 here says work function of a metal is 2.7 electron volts. So we are asked to find which of the following pairs, okay, they gave us options, correspond to we are asked to find the threshold frequency and the threshold wavelength. Okay, we are given the Planck's constant, we are given C, which is the speed of light in vacuum, and we are given our 1 electron volt to 1.6 times 10 raised to the power minus 19. Okay, so quickly, our work function, which is W naught, is given in electron volt. So we convert it to joules. And that will be 2.7 times 1.6 times 10 raised to the power minus 19. That will give me 4.32 times 10 raised to the power minus 19 joules. Okay, so you recall this formula that says W is equals to HF naught. We are asked to find the threshold frequency. F naught is the threshold frequency. So if we make F naught the subject of the formula, I'm going to have W over H. Okay, so F naught is equals to W over H. My threshold frequency, which is F naught, is equals to the work function over H. So my work function here is 4.32 times 10 raised to the power minus 19 over H, which is a Planck's constant, is 6.6 times 10 raised to the power minus 34, and that will give me 6.55 times 10 raised to the power 14 hertz. Don't forget that frequency is measured in hertz. The unit of frequency is hertz. So we have answered the first question. The second question says we should find the threshold wavelength. So you recall also that W naught is equal to HC over lambda, which is the threshold wavelength. Here is the threshold wavelength. So if you make this the subject of the formula, we are going to have HC over W naught. Our HC, H is a Planck's constant, which is this. Our C is the speed of light, which is 3 times 10 raised to the power 8 over W naught. We just calculated that to be this. 4.32 times 10 raised to the power minus 19. That was what we got here as W naught. So multiply this and divide will give us 4.5 times 10 raised to the power minus 7 meters. So the threshold wavelength is equal to 4.5 times 10 raised to the power minus 7 meters, and the threshold frequency is 6.55 times 10 raised to the power 14 hertz. Question 8 says, calculate the frequency of the photon. We are asked to calculate the frequency whose energy is required to eject the surface of the electron to kinetic energy. Okay, we are given the kinetic energy in electron volts, and we are also given the work function from the question, and we are asked to find the frequency. Okay, so from the question, the kinetic energy is given in electron volts. So first we need to convert that to joules. So how do we do that? 1 electron volt is equals to this. So we multiply by 1.6 times 10 raised to the power minus 19 joules. And that will give me 3.04 times 10 raised to the power minus 35 joules. I believe that is clear. Now, the work function, which is this, also is given in electron volts. So we convert that likewise to joules by multiplying with the same value, and that will give me 2.128 times 10 raised to the power minus 35 joules. Okay, so we go ahead. It said, so we go ahead and from this formula that says E is equals to EK plus work function, we recall this formula. So we put in our EK, which is the kinetic energy, to be 0.4 times 10 raised to the power minus 35 plus the work function, which is 2.128 times 10 raised to the power minus 35. Now, addition of this will give me 5.168 times 10 raised to the power minus 35 joules. And that is our E, which is the energy of the photon. But the question says we should find the frequency, not the energy. So you recall this equation, E is equals to HF. So from here we make F the subject of formula, and we have E over H. So our E is 5.168 times 10 raised to the power minus 35 all over H. Our H is a Planck's constant, which is 6.6 times 10 raised to the power minus 34 joules per second. Okay, so if we divide this by this, we are going to have 7.83 times 10 raised to the power minus 2 hertz. Frequency is measured in hertz. I believe that is clear. Okay, so question 9. We have this. The uncertainty in determining the duration, particular energy level. Okay. The duration, that's the change in T. Change in T is this. Delta T is equals to 2.0 times 10 raised to the power minus 9 seconds. And we have this H over 2 pi. So you recall that delta E is greater or equals to H over 2 pi delta T. So the question here is saying that we should determine the energy, uncertainty in energy, which is delta E. And this will give us our H over 2 pi already we've been given. Then delta T, and this will give us 1 times 1.054 times 10 raised to the power minus 34 all over delta T, which is this 10 raised to the power minus 9. If we divide that, we have 5.27 times 10 raised to the power minus 26 joules, which is equals to the uncertainty changing E. Okay, so for the last question, the wavelength, which is lambda, is equals to this, and that's 5 times 10 raised to the power minus 7 meters. This is a work function. W naught is equals to 1.90 eV. Now, we need to convert this to joules. You multiply by 1.6 times 10 raised to the power minus 19, and that will give us 3.04 times 10 raised to the power minus 19 joules. Okay, so we are asked to calculate the photon energy. E is equals to HF. So the photon energy is equals to HF, and the same thing as HC over lambda. We know our lambda, we know our H, and we know our C. So we just go ahead and write E is equals to HC over lambda, which equals to our Planck's constant, and the C, which is 3 times 10 raised to the power 8 over the lambda, which is 5 times 10 raised to the power minus 7. And this will give me 3.96 times 10 raised to the power minus 19 joules. So we have answered the first question, the photon energy. The next question says the kinetic energy of the most energetic particle. So we recall that E is equals to W naught plus EK. So if we make kinetic energy the subject of the formula, we will be left with E minus work function And we just calculated our E to be this minus the work function 3.04 times 10 raised to the power minus 19. So if you subtract this, we are going to have 9.2 times 10 raised to the power minus 20 joules. And that answers question 3 too. Now, the last question, this is the stopping potential. You recall from this equation, stopping potential is equals to EK over E and is equals to HF minus V, work function over E, depending on what we have. Okay, so I'm just going to go ahead and use this. Since I have the kinetic energy, 9.2 times 10 raised to the power minus 20 over E. Our E is the charge, 1.6 times 10 raised to the power minus 19, and this will give me 0.575 joules. Okay, let me write that properly. 0.575 joules. So the stopping potential is equals to 0.575 joules. I want to believe that's very, very explanatory. In case you still need explanations on energy quantization, don't hesitate to watch the full video on energy quantization. And don't forget to subscribe.